The stars produce mysterious bursts of monstrous X-rays, solar flares out of this world.
So the strongest flares we've seen are 10,000 times stronger in the X-ray band than the strongest flare ever seen in the sun. When we looked at 1,000 young suns simultaneously in the Orion Nebula, we found that they're typically flaring at this level once or twice a week.
Solar storms like the one that hit Quebec can release as much energy as 1 billion atomic bombs. The star's Feigelson studies produce flares 10,000 times more powerful. The Hubble telescope catches an eruption on a star 450 light-years from Earth. This flare is so huge, if it hit a space colony, it would take out more than their power. It would take out their planet. Scientists call it a superflare. It's not just one star that creates superflares. There are regions of space where nearly all the stars are doing it. 1,500 light-years away is the Orion Nebula. It's a brilliant haze of gas and dust. In X-ray, the dust disappears, leaving only the stars. This X-ray movie was filmed over 13 days. Each tiny flash is a flare thousands of times more powerful than any produced by our sun. These stars are just like the sun, except much younger.
This cluster was formed about 1 million years ago. Now, that may sound like a long time ago, but compared to the sun, which is 4.5 billion years old, these are very, very young stars.
The Orion Nebula is where new stars are born.
They'll all become like our sun. They're just like our sun was when it was a young star.
Space scientist Gibor Basri wants to know why young stars create such huge flares.
If you take a given kind of star, say a star like the sun, there's a direct correlation between how much magnetic activity you see on that star and how fast you spin it. The slower the star spins, the less activity it has on it.
Like the sun, these stars create huge amounts of magnetic energy because their equator spins faster than their poles. The faster a star spins, the bigger the arcs, and the stronger the flares. And young stars spin very fast.
Our sun goes around about once a month. When it was very young, it went around every couple of days or a few days. So that's how much it's slowed down. And that means that the sun is now much less active than it was then.
Feigelson describes a sun we wouldn't recognize.
When the sun was a baby star at 1 million years old, it was 3 times bigger. It was a ruddy orange color. It had huge star spots that whipped around every few days, rotating much faster than it is today. And the magnetic fields, which you wouldn't see with your visible eyes, but you'd see with an X-ray telescope. The magnetic fields would be 10 times the size of the star, crackling and seething with explosions.
Some scientists think if it wasn't for the violent early sun, the Earth and all the planets in the solar system might not be here. 4.6 billion years ago, the solar system is just a cloud of gas and dust racing around the young sun. How it transforms into the solar system we see today is still a mystery.
So the disk is full of dust, and it's sort of the consistency of cigarette smoke. These are really tiny dust particles. We're really pretty puzzled about how you get from dust bunnies to asteroids. It's easy to stick snowballs together, but it's not so easy to stick sandballs together.
Basri thinks the violent young sun helps build all the planets in our solar system. Giant solar storms rip through the disk. The dust particles are forced together. Over time, they fuse and grow. The first embryonic planets are born. Eventually, the solar system is formed. And as the sun ages, it begins to slow down. If it hadn't calmed, life in the solar system might never have developed. Yet when the sun coughs, the Earth still shudders. There's little shelter from the effects of a massive solar storm. The only way to protect our electricity network is to shut it down before the storm strikes. But how do you predict a solar tantrum? Solar storms are a serious threat to our high-tech lives in the 21st century. The race is on to predict when and where the next one will strike. In September 2006, Japan launches the Hinode satellite. Its 3-year mission is to map the sun's complex magnetic fields. The information it sends back could prove key to forecasting solar storms. Hinode orbits 370 miles above Earth. Its camera peers straight into the sun's atmosphere. It returns the clearest pictures ever of the sun's surface. In December 2006, Hinode captures this groundbreaking footage. A magnetic arc snaps, and a huge flare erupts. It blasts into the solar system at more than 1 million miles an hour. Carol Shriver uses data from Hinode to generate the first computer model of a solar storm before it erupts. A detailed map of the sun's complex magnetic fields.
What drives these large solar flares is the magnetic field, and specifically its electrical currents running through the magnetic field. So each one of these strands is essentially an electrical current prefabricated in the interior of the sun, breaking through the surface and becoming visible, and then ready to power a flare.
Where the magnetic fields intertwine the closest, the currents are strongest. Shriver replicates these electrical currents in 3 dimensions.
If we tilt this, we can suddenly see that these electrical currents come up from one place, go up by something like 20,000 kilometers above the solar surface, and come down again.
The model shows a red river of energy equal to 1 billion atom bombs. When the flare erupts, it releases that energy in seconds.
The amount of energy that goes off in this flare is simply astounding. It's the equivalent of 1 million times 1 million atomic bombs going off at the same time.
Before, a red river of current thicker than the Earth. After, almost nothing. This is exactly what happened 3 days before the Quebec blackout. If Hinode can spot these densely packed lines of magnetism before a flare explodes on the sun, scientists might be able to predict when the next solar storm will strike. Until that technology arrives, space weather forecasters use a method of analyzing the sun's activity developed almost 400 years ago. Sunspots. Sunspots form because the sun's atmosphere is hotter than its surface. The magnetic arcs block the atmosphere, making the sunspots burn cooler than the surrounding surface. 6,300 degrees versus 10,000 degrees. Sunspots come and go in an 11-year cycle of maximums and minimums. Solar minimum has few sunspots and the fewest flares. At solar maximum, 200 sunspots or more, all firing magnetic arcs. A week before the Quebec blackout, astronomers identify a group of sunspots on the eastern edge of the sun's surface. The blackout occurs during a solar maximum. The next maximum is around the corner, in 2012. The sunspot cycle tells us the gun is loaded. It doesn't tell us when or where the bullet will strike. Once the magnetic arcs cross, the trigger is pulled and a flare explodes. It reaches Earth in just 8 minutes, too fast for a warning. But the most damaging part of a solar storm is slower. A coronal mass ejection can take up to 4 days to arrive. If we know when the solar surge will hit, we can save the electricity network by shutting it down. At the Space Weather Prediction Center, scientists keep a watchful eye on the sun. They're looking for any increase in activity, including the buildup of sunspots.
Well, the forecaster today is looking at the data, trying to understand what the sun is doing right now, and then making predictions of the effects on Earth.
Solar satellite technology is young. It's observed the solar maximum only 3 times. Space weather forecasting is where Earth weather forecasting was 50 years ago.
If you were trying to predict a hurricane, if you didn't know anything about the speed of the winds and you didn't know anything about the atmospheric pressure at the eye of the storm and some of those types of things, that would be fairly comparable to where we are now in space weather.
You can see a hurricane coming, not a solar storm. Once it leaves the sun's surface, it's practically invisible. It can hold 10 billion tons of matter, but it's spread over millions of square miles. Just a handful of atoms in every cubic foot.
You couldn't see one of these storms arriving at Earth with the naked eye. They are so dilute that they are actually better than the kinds of vacuums that we can create under laboratory conditions.
Satellite instruments are sensitive enough to detect solar storms. But there's a catch. If one heads straight toward us, it's very difficult to tell how fast it's traveling. It's like the batter in a baseball game. As the ball hurtles toward the hitter, it's impossible to judge its exact speed. 3 strikes, and he's out. If scientists misjudge the speed of a solar storm, 1 strike could take us back to the Dark Ages. To help solve this blind spot, in 2006, NASA launches a 2-stage satellite called Stereo.
Stereo's great. We're going to be able to watch coronal mass ejections from perspectives that we've never been able to see before. And most importantly, it would be the one that allows us to watch the event happen along the Sun-Earth line.
After launch, the satellites separate. They use the moon's gravity to reach their orbits, flanking the Earth. The 2 near-identical satellites orbit the sun, but one of them is slightly ahead of the other. They give the first 3-dimensional stereo view of the sun. Scientists can now forecast very quickly if and when a solar storm is going to hit the planet.
It will improve the timing in particular of the forecasts that we would try to make, to mitigate the consequences of that as it went by the Earth.
NASA hopes that Stereo's information will lengthen early warning times from just a few hours to a couple of days. It could prevent blackouts like Quebec from ever happening again. One day, advanced satellite technology might even predict solar storms before they're born.
It won't be next year. It may be a few years, but it's doable now. We've been moving ahead very rapidly.